We start this slide with the computation of the residue of our function at infinity. The residue at infinity is in turn defined by the expansion of our function at the vicinity of infinity. So suppose at infinity our function looks as follows. f of z is equal to cn times d to the power of n plus cn minus 1 z to n minus 1 plus c naught plus c minus 1 over z plus and so on. So the residue at infinity is found as minus c minus 1. So to find the residue at infinity, we simply need to expand our function at large values of z. We kind of already touched this subject before when we were discussing the multiple valuedness of our function at the beginning of our discussion. We found the asymptotics of our function up to some mysterious cubic root of -1. Back then we were unable to decipher it due to its obvious triple-valued nature. But now we have all the means to do so, since we picked up a particular regular branch of this cubic root. The easiest way to do so is to set z large, real and positive. As you clearly see, the number under the cubic root for large positive values of z becomes negative, so we have to interpret it correctly. And so we use the same technique. We pick up some x0 reference point on the upper bank of our branch cut and write down the standard formula for the regular branch. f of z equals the modulus of the ratio of f of z and f of x0 plus I0 times f of x0 plus I0 times e to I delta argument of f. To find the change of the argument of our f function, we draw a contour connecting the reference point and the point at plus infinity, and trace the changes of the arguments of the constituents of our cubic root function. So delta argument of 1 minus z. Obviously, the arrow representing this number rotates by pi in the clockwise direction. So the corresponding change of the argument is negative pi. The arrow 1 plus z obviously doesn't rotate at all, and the corresponding change of the argument is 0. So the total change of the argument of our function is simply negative 1/3 times negative pi. So it's pi by 3. Since f of x plus I0 is positive due to our choice of the regular branch, the modulus of x plus I0 is also positive, so we can cancel out the corresponding expression in the numerator and denominator of our formula and end up with much simpler expression. Modulus of f of x times e to I pi by 3. The focal point in this formula is the modulus sign, since we remember that the modulus of the cubic root is equal to the cubic root of the modulus, which makes things positive under the root. And this in turn allows us to use real-valued analysis to perform 1 over x expansion. So let's do this. f of x, or the modulus of f of x, is equal to 1 over cubic root of the modulus of 1 minus x times the modulus of 1 plus x squared. But 1 plus x squared is positive, so we don't need modulus sign here. So we just write 1 plus x squared. And then under the modulus sign, we have 1 minus x, the negative expression. So we remove the modulus sign and write it as x minus 1 times x plus 1 squared. And then we have a perfect positive expression under our cubic root and perform standard 1 over x expansion. So we factor out x from each of the bracket and put it out of the cubic root. So we get 1 over x times 1 minus 1 over x times 1 plus 1 over x squared. So let's rewrite it in the most suitable form. It's 1 over x times 1 minus 1 over x to the power of minus 1/3 and 1 plus 1 over x to the power of minus 2/3. But look at this expression closely. We are hunting for 1 over x expansion, but it's already here in front of these brackets. So if we, for example, use real-valued analysis to perform the further expansion of the brackets, we'll obtain higher order terms like 1 over x squared and so on, but we don't need them. We need just the senior 1 over x term. So we can discard 1 over x in each of these brackets and leave it just the whole expression as 1 over x. And since x is equal to z, in our case, then we get the leading order expansion of our f of z function. It's simply e to I pi by 3 divided by z. And hence we extract our c minus 1 coefficient, which is simply e to I pi by 3, and as a result the residue of our function, which is now minus e to I pi by 3. Therefore, our closed contour integral is now basically computed. It's equal to minus 2 pi I times e to I pi by 3. And now recall the relation connecting this closed contour integral with our original integral. It's equal to I times 1 minus e to 2 pi I by 3. And as a result, we obtained the value of our original integral. So to make things simpler, let's factor out e to I pi by 3 on the right hand side of our equation. And we see that in the brackets we collect minus 2i sine pi by 3. And now the equation looks good because we can cancel this complex number e to I pi by 3 from both parts, as well as minus 2i, and end up with pi over sine pi by 3, or 2 pi over the square root of 3. So that's it, the integral is done. The only thing which is left to discuss is the integrals round the infinitesimal circles at the endpoints of our contour. In the beginning of our discussion, I told you that they vanish as the radii of the circle tends to 0, but left the statement without the proof. So now let's prove that the integral around the right circle, round point 1, actually vanishes. So let's make a suitable change, z equals 1 plus epsilon, where epsilon is small parameter, and parameterize epsilon as the modulus of epsilon times e to I phi. As a result, dz is equal to epsilon e to I phi I d phi. This way we turned our integral along dz to the integral along d phi, where phi changes from 0 to 2 pi. So let's plug this change into our cubic root. So f of 1 plus epsilon now is equal to 1 over cubic root of negative epsilon times 2 plus epsilon squared. But in the second bracket, we can discard epsilon as a small parameter. So in the end, we'll obtain 1 over the cubic root of negative 4 times modulus of epsilon times e to I phi. So what we get is the following expression. Let's collect all the pieces together and put them into our integral. And now we see that the whole thing consists of two parts. The integral part over the angle d phi, which is independent of epsilon, and the prefactor, which is modulus of epsilon to the power of 2/3. So the behavior of the integral as a function of epsilon is simply epsilon to the power of 2/3. And obviously the whole thing vanishes as epsilon tends to 0. And this completes our proof. In completely analogous manner, you can prove that the integral around the left infinitesimal circle also vanishes. So now let me summarize the principal steps of our method. Step 1. Choose the branch cut coinciding with the contour. Check if this branch cut actually makes your integrand a single-valued function. Step 2. Deform the contour and fixate the regular branch of your integrand. Step 3. Close your contour and express the original integral through this closed contour integral. And finally, step 4. Use the residue theorem to compute this closed contour integral. So I hope you got the general idea of the methods from the example we just thoroughly worked through. In our future examples, we'll discuss more details and tricks to polish the technique and help you build a better command of it. So stay tuned.